Hello friends, I Madhuri Tayal. Today we are going to study the topic asymptotic notations, under that big O notation. In the previous lectures we have seen regarding the time complexity, then the space complexity and various graphic functions. Now here today we will be studying the different kind of functions under the asymptotic notations. So first it is a big O notation, then the omega notation, and then the theta notation. So now let us start with the topic big O notation. So there are different algorithmic complexities. They are divided into three types, that is in worst case, then it is in best case, and it is in average case. When we say worst case analysis, means in worst case how we can represent the complexity of the given code. So worst case complexity is the function defined by the maximum number of steps taken on any instance of size n. So one example, like in linear search, when we want to find a number in a given array, we have to search, or we have to compare each element of that array with the item, and then that way we can compare maximum n number of operations. So here that worst case complexity of that code or that algorithm will be O of n. So this we call it as the worst case complexity. Now suppose for the same algorithm, if I am getting that item on the first position itself, so I will be calling it as the best case complexity. So here it is the second kind of complexity, is a best case complexity. So the function defined by the minimum number of steps taken on any instance of size n, I will be calling it as the best case complexity. The third category out of this or remaining, that is the average case complexity, means if it is not worst case, if it is not best case, that means it is in between. So that is average case complexity. The function defined by the average number of steps taken on any instance of size n will be called as average case complexity. So suppose for the binary search operation, average case complexity we can make it at, suppose we are getting that item on the middle position. So half number of operations, so it can be O of log of n to the base 2. Now we can show this thing, the three analysis of the complexity functions on the graph paper. So this diagram shows on x-axis the input size and on y-axis the number of steps. So now please verify the three complexities how they are that we have shown on the graph paper. So when you compare, your worst case complexity always will be highest on the side, then the average case complexity and the best case complexity. Now we can categorize all these three cases of complexities in three parts or in three notations. So let us go ahead. Just verify before that, we do have a complexity scale of the different functions. We have studied in the previous video that the various functions or the growth of functions of the different values. So it is 1, then log n, then root n, then n log n, then n square, then n cube, then 2 to the power n, then 3 to the power n, and n to the power n. So this is nothing but a complexity scale, and this scale will be helpful for us while solving the various problems of the different notation. I'll be using this complexity scale for every notation, that is for the big O notation also, that is the best, that is the what we can call it as that big O notation for the extreme case, that is what we can call it as the extreme case, then the omega notation, that is for the best case, and the theta notation. So that is that will be going to using this whole scale. Now let us understand the big O notation, that is for the upper bound. So big O notation we can define this big O notation, it is for upper bound. So the function f of n equals to O of g of n if and only if there exists the positive constant c and n0 such that your f of n less than equals to c into g of n for all n greater than equals to n0. Now let us understand what I have written here. If I am saying f of n less than equals to c into g of n, if suppose this condition is satisfied, then only I can say that for this equation that f of n equals to O of g of n. Now let us take one problem so that we can understand this thing. Now let us take f of n equals to 2n plus 3. Now if I mention this 2n plus 3 as f of n, now just try to identify roughly one value on the right hand side which can satisfy this equation. I have written just 10 into n. Put the value of n as just 1. So you will be getting 2 into 1, 2 plus 3, it will be 5. On the right hand side it will be 10 into 1, 10. So from this equation we can identify that the value is, or this equation is right. That means in this case this left hand side of this equation can be f of n, then the 10 value will be c and this n value will be g of n. Now even this 10 can be replaced with any other value, means the greater value only. So even it can be 7 also. So you have to verify that for every n greater than equals to 1 value your equation should be satisfied. So for the place of 10 it can be 10, it can be 10,000, it can be 20,000 also. So if we are achieving this, that means that way that constant will become c, and if this equation is satisfied then we can say the complexity of this code equals to f of n equals to O of g of n, means is for 2n plus 3 your complexity will be O of order of polynomial n is 1, so it will be O of n. Now let us analyze this problem in detail. Now f of n equals to 2n plus 3. Now 2n plus 3 less than equals to 2n plus 3n. Now I had taken on the right hand side, after 3 I had taken n value, so that I am just finding the minimum value where this equation gets satisfied. So this is 2n plus, for this 3 that is on the right hand side I have put n. So in the next case I will be getting 2n plus 3 less than equals to 5n. So this is nothing but this equation is true for all greater value than 5. It is equal for, if you will be putting n equals to 1, it will be 5 equals to 5n, means after 5, 6, 7, 8, 9, 10 for all equations this whole equation gets satisfied. So we can say that the complexity of this code will be O of n, because your f of n less than equals to c into g of n is satisfied. So if you can verify this one on your complexity scale, so you find you'll be getting that the n value is in between, and from the left hand side it is a lower bound that starts from n to root n, then log n, then 1. So this is from n to 1, that is a lower bound, and from n to right hand side it is upper bound, that is n log n square, n cube, 2 to the power n up to n to the power n. So this way we have categorized your O of n in in 2 bounds, that is from n to left lower bound and from n to right the upper bound. So this is the value that we are achieving, that is big O notation. For 2n plus 3 it is big O of n. So this question can be asked like, prove that the running time t of n equals to 2n plus 3 is O of n. So this way even if the question is asked we can answer like this. So going ahead, so if the same question is given like prove that the running time t of n equals to 2n plus 3 is O of n, so we can solve like this. Already I have shown in the previous slide. So it is that only that 3 part on the right hand side we have made n, and then it becomes 5n. So total your notation is theta of n. Sorry, it is a big O of n. Now let us take another problem. Prove that the running time t of n equals to 2n plus 3 is O of n square. Now the same problem, but in the previous problem we have seen this 2n plus 3 is O of n. Now we are saying it is O of n square. Now let us verify how this is true and how we can show it. So let us go ahead to solve it. Let us take g of n equals to 2n square plus 3n square. How I have made it? Because I want to prove that in the polynomial of degree 2. So I had taken the g of n for the polynomial degree 2, that is 2n is replaced with 2n square, and now your right hand side 3 is with the 3n square. So I got the value or this relation 2n plus 3 less than equals to 5n square. It should be true for all n values greater than equals to 1. So it is true. Even 5, 6, 7, 8, 100, 1000 if you will be taking, your equation will be true. So here 2n plus 3 will become your f of n, your 5 will become c, and your n square will become g of n. So again you verify this thing on your on complexity scale. Yes, it is true, and please verify the scale, that is n is in between, then lower bound on the left hand side and the higher bound, upper bound is on the right hand side. So here please verify that already we have proved that 2n plus 3 is O of n, and T of n equals to 2n plus 3 is O of n square. We can verify that this n square is on the right hand side of your n. That means it is going right, means n, then n log n, then n square. Whenever you are going to the upper side of your complexity in your big O notation, it is right, because you are going upper side, you are not going the lower bound side, you are not going left. So even for n, if it is true, it can be true for n square, it can be true for n cube also, but please verify both are right, that is T of n 2n plus 3 is O of n, and T of n 2n plus 3 is O of n square. Both are right, but the optimal value is to be chosen, therefore this 2n plus 3 is O of n. So answer for this question is that even we know that 2n plus 3 it is O of n, but still the upper degree will always okay, because that will be again a solution, but the optimal solution will be O of n. So this way this problem indicates that even for the same question, if it is asked that T of n equals to 2n plus 3 is O of n cube, even the answer is right. Okay, so proceeding further for the next problem. Now you can verify this, again the complexity scale. We have just verified f of n equals to O of n, even f of n equals to O of n square, even f of n equals to O of 2 to the power n, but the wrong value is f of n equals to O of log n. Why? Because this O of log n, it is on the left hand side of your n. Below n is not okay, above n is okay and right. So we'll be choosing the closest one. Therefore the complexity of this code will be 2 of 2n plus 3 is O of n. Now one more problem, that is prove that the running time of T of n 2n square plus 3n plus 4 is O of n square. Again you write your complexity scale and then try to solve your problem. F of n is given, that is 2n square plus 3n plus 4. Now let g of n, you can choose the value, because it is 2n square, so you can take on the right hand side 3n square plus 4n square. With this kind of analysis, I want to try the minimal value that will satisfy this equation, and then all the greater values definitely will satisfy this equation. So it will become 2n square, 3n square plus 4n square, it will be total 9n square. So your f of n will be on the left hand side, then 9 will become your c, and your n square will become g of n. Now this 9n square is true for all n values which are greater than equals to 1. Even at the place of 9 there can be 10, 11, 12, 13 and all that, but 8 is not possible because it's satisfied with the value of n equals to 1. This is equals with this 2n square plus 3n plus 4 equals to 9n square when you will be putting the value of n equals to 1. So if this is satisfying, that means we can say that f of n equals to big O of g of n. That means here the degree of polynomial of 9 of n square, it is 2. So your f of n equals to O of n square. Hope you understood. Now the last problem for today, we have to prove that for this function n cube plus 20n plus 3, it is not O of n square. We have to prove that it is not O of n square. Even just from the analysis of our complexity scale, I have already told you that we can go from n to n square to n cube. We can't go on the lower bound. So from n cube to n square, it won't be there, because in this problem the highest degree of your n is 3. So here it is mentioned not of n square, you have to prove it. Okay, so let us take according to the big O notation, it is f of n less than equals to c into g of n. On the left hand side you keep the value, on the right hand side there is a n square plus 20 n square plus n square. So again we had taken the value, because we have to prove it is not of O of n square, so we had taken n square as the main polynomial on the right hand side, and we are balancing with that n square. So we are getting the value on the right hand side is 22 n square. So when we put the value of n is equals to 1, so will be, yes, we find that the equation is true. Again for n equals to 2, your equation is true, but it is not true for all n values 100 and greater. Is it okay? That means we can verify that for the value n equals to 100, and if it is not true, that means whatever is given is not true. So we can verify that from n cube we are moving down to n square, so definitely it is wrong, and this way we can prove this question. So these are some more questions that you can solve for practice. Again you can prove 2n square equal to O of n square, then this big equation, second problem, then the third problem, then fourth problem. It is said that 2n cube plus 2 is not equal to O of n square, and n to the power 2.1 is not equal to O of n square. So you can solve all this question for practice purpose. So thank you friends for watching this video. In the next topic I'll cover the asymptotic notation with omega notation and many more problems. So keep watching the lectures and kindly give the feedback. Thank you.